Rolling motion can be fairly complicated, but we're going to try to simplify it, break it up into rotation and translation, because it's really a combination of those two things. Let's think about what rolling motion is. I have a roll of tape here, and if it's sitting on a surface and rolling, well, what's happening to the point that's in contact with that surface? It's not moving at all. The point in contact with the surface is basically at rest. And the point up here, farthest away from the axis of rotation, is rotating about this point that's in contact with the surface. That's the axis of rotation. The point that's farthest away is moving the fastest. And the point halfway down the center of my roll of tape is moving slower, and the point in contact with the ground is actually not moving at all in this direction. We call this rolling without slipping. So the object rolls without sliding on the surface. The point of contact never moves. And the reason rolling without slipping is important is because there's a relationship between the rotational speed and the translational speed when there's no slipping. If there's slipping, if this object is sliding along the surface as it's rolling, or maybe it's spinning faster than it's rolling, like a car about to burn out from when the light turns green, spins its wheels, and then it starts to move. Well, those wheels are spinning much faster than the car is actually moving, and it's burning rubber and creating smoke and leaving marks on the street. Well, that's slipping, right? The tire's slipping as the car is moving, and there's no relationship between the rotational rate of the tire and its translational speed. But if it rolls without slipping, there's a relationship, and that's what we're going to take a look at today. That's what's important. So just to recap, rolling without slipping means our object is rolling, and the axis of rotation for our object is actually that point right there. That point is not moving at all with respect to the ground. It's stationary. The center of our wheel is moving to the right with some speed. I'll call it V center of mass because that's the center of mass of the wheel. And a point up here at the top of the wheel is moving with how much speed? Twice as much as the center of mass, because it's twice as far away from the axis of rotation. Remember, V is equal to R omega, as we saw in the previous video. So we have an object here that's rotating. Every point on that rigid object has the same omega. But the farther away you are from the axis of rotation, the faster your linear speed has to be to keep up, to cover a bigger distance in the same amount of time. So this is rolling without slipping. Let's take a look at what it means just to rotate and what it means just to translate. So if we have pure rotation, let's see what that would look like for our wheel. In pure rotation, the object is not moving, it's only rotating. So for my roll of tape, the center of my object never moves, but my object just rotates about that center point. Pure rotation, no translation. But every point other than the center is moving because the object is rotating. And the farther away we get from the center, the faster they have to move to complete a revolution in the same amount of time as all the other points on our wheel. So a point at the top would have a certain speed to the right if our object was rotating clockwise, or I should say, if our object has an angular speed omega that points into the page. And that's just some arbitrary speed. I'm going to call it VCM. And a point at the bottom of my wheel would have the exact same speed in the opposite direction. It's the same distance from the axis of rotation. So the speed is the same, and as that wheel rotates, it would point to the left. Now, what would happen if we had pure translation? So our object is not rotating at all, it's just moving, translating. Well, every point on our object would be moving with the exact same speed. And I'm just going to call that VCM. We'll just pick a speed. So we can move this with a certain speed to the right, and every point, the top, the middle, the bottom, every point will be moving to the right with the same speed. Or we could have pure rotation, where I rotate this, and the center of the wheel doesn't move at all. And the top is moving to the right, and a point on the bottom is moving to the left. So we could have pure rotation, and we could have pure translation. And what happens if we combine these? What does that equal? Let's take a look at what's happening at the point at the very bottom of the wheel. We have a velocity to the left and a velocity to the right, and we add those together and we get v equals 0 at that point. Let's take a look at what's happening to the center of our wheel. We have v equals 0, and v is equal to v center of mass to the right. We add those together, and we get v center of mass to the right. And what's happening with the top of our wheel? We have v center of mass to the right, v center of mass to the right. We add those together, and we get 2v center of mass to the right. Well, does that look familiar? Let's take a look. We said that when we had rolling without slipping, that was the exact situation we had. V is 0 at the point of contact where our wheel is touching the ground. The center of our wheel is moving with some speed to the right. We're just calling that v center of mass. And the top of our wheel is moving with twice that speed to the right. And that's what we have here. So when we combine pure rotation with pure translation, we get rolling. So we can take this complicated motion, this rolling motion that's fairly complicated. We've got an object rotating about an axis of rotation here that touches the ground, fairly complicated motion. We could treat it as that. We could treat it as an object rotating about this point. It's a little more complicated. Or we can say, instead of treating it like one object rotating about this point, I'm going to pretend this object magically splits into two. One that's just spinning and not going anywhere, and the other one that's moving, translating without spinning. And it's exactly the same as far as energy is concerned. So that's typically the way we would solve an energy problem with an object that's rolling. We would pretend it magically splits into two objects. One that moves without rotating, and one that rotates without moving. So in order to do that, I have to prove to you that there's a relationship between this v center of mass and omega, how fast our object is rotating. So let's take a look at a wheel that rolls just a short distance to the right. On the left side, I've got my wheel in its initial location. And I'm just going to mark 2 points on the wheel. I'm going to mark the point that's in contact with the ground. We're going to call that point A. And some point up here, we're going to call that point B. And there's an arc length, S, the arc length between A and B. Now I'm going to get out my green paint, and I'm going to paint the edge of that disc, that wheel, green. And while my paint is wet, I'm going to roll the wheel forward a little bit. I'm going to roll it forward until point B is the one that's in contact with the table. That means that point A is up here. And when I do that, the table gets painted green. So how far did my wheel move to the right? This distance has to be the arc length, as you can see by my paint trail. When the wheel rotates over, the center of mass of my wheel moves by a distance s, by the arc length between those 2 points. And I know that the velocity along the rim has to equal the radius of my wheel times omega. Because the rim covered a distance s in the same time period that the center of mass moved a distance s, I know the velocity of the center of mass is the same as the linear velocity on the rim of the wheel. So my relationship, the velocity of the center of mass, has to equal the radius of my wheel times omega, the rate that it's spinning, the rotational rate. These are connected when I have rolling without slipping. And this is important because now I know how to split up my problem. I say rolling is kind of complicated. I'm going to pretend this rolling object actually magically splits into 2 objects. One that is pure rotation. How is it rotating? With angular velocity omega. One that is pure translation. How is it moving? With speed v center of mass. But those aren't 2 arbitrary values. They are connected. They are tied together by this relationship. V center of mass equals r omega.